Just now we discussed what gravitational force is. Gravitational force is the force acting between any two objects that are separated at a distance. Now, earlier this gravitational force was linked to only the planetary objects, but when Newton came into picture, he took this idea and he formulated his universal law of gravitation, and he said that any two objects, be it celestial or terrestrial, they are going to experience this force of gravity or the gravitational force, and therefore he called his laws the universal law of gravitation. Now, as per this law, as you can see, there are two objects. So, any two objects of masses m1 and m2 that are separated by a distance r between the two centers, they get attracted to each other with a force, and that force is directly proportional to the product of masses. So, F is the gravitational force, it is directly proportional to m1 into m2, and it is also inversely proportional. The force is inversely proportional to the square of the distance between them. Therefore, we say F is inversely proportional to 1 by r square. If you combine these two conditions together, you get F is directly proportional to m1 m2 by r square. Now, you can remove this constant, this proportional sign by introducing a proportionality constant. So, F is equal to g m1 m2 by r square, where g is the constant of proportionality and it is called the universal gravitation constant. Its value is 6.67 into 10 to the power minus 11 Newton meter square per kilogram square. So, the law of gravitation, it is called universal because it holds true anywhere, celestial place or a terrestrial place, and it holds true at any instant of time. So, it is independent of time, it is independent of place, hence it is called the universal law of gravitation. So, what is the use, what is the importance of gravitational force and the law of gravitation? The gravitational force binds the solar system together, and it is also the cause of planetary motion. Had there been no gravitational force, all the planets would have gone haywire and they wouldn't have been able to form a structured family where they revolve around the sun and rotate around their axis. All these things would not have been possible had there been no force of gravitation. So, the first important role that the law of gravitation or the gravitational forces play is that they bind the solar system together and keep the planetary motion going. The tides that you experience, the tides that you see in oceans, the high tides and the low tides are a result of gravitational pull that the moon applies on the water of the earth, of these oceans on the earth. The ocean water gets attracted by the moon, it rises up. So, the force is not as much, so it does not just go and reach the moon, it just rises and then it falls down. So, there are times when there is high tide, so that is a time when the moon is closer and there is greater force of attraction, so the tides go high up. The low tides are when the distances are further apart, so the tides do not rise as much. So, you have the tides resulting due to the gravitational pull of the moon. Now, the presence of atmosphere around the earth, you have a 200 kilometer envelope of atmosphere that surrounds the earth, and that is what keeps the life on earth going, and that is because of the gravitational pull. So, all the air molecules, the molecules that are there, the atoms, the gases that are there in the atmosphere, they experience the gravitational pull of the earth, and that keeps them bound to the surface. So, they stay within an ambit, within a 200 kilometer range, they circle the whole earth, they envelop it and keep it intact. It gives us the oxygen that we breathe, it protects us from the harmful rays of the sun. So, the atmosphere, the presence of atmosphere around the sun, around the earth, is due to the gravitational pull of the earth. Any object that you throw up in the sky is going to come back to you. That is again a result of gravitational pull of the earth. So, it is not like you throw a bottle up in the sky and it never comes back to you. You throw it, it will come back to you. So, that is again a result of the gravitational force that the earth applies on any object that is there on its surface or above it. So, the earth pulls any object, and that makes anything that is thrown up to fall down and come back to the surface of the earth. So, that is the importance of the law of gravitation, the gravitational force and its effects. So, now let us take up the first question, which says that you have to calculate the force exerted by the earth on you if the mass of earth is 6 into 10 to the power 24 kg and the radius is 6400 kilometers. Now in place of you, it is going to be me here. So I'll put my mass and calculate the force that the earth exerts on me. Similarly, you can do it for yourself. So this is the mass of the earth and the radius of the earth that's given. The mass of body is going to be small m, and it's going to be, for my case, it's going to be 65 kgs. So what is the force exerted by the earth on the body? It's the gravitational force, which is given by G is equal to F is equal to G mm by r square, right? Now what is G? G is 6.67 into 10 to the power minus 11. The mass of earth is 6 into 10 to the power 24. Small m is 65 kgs. The radius is 6.4 into 10 to the power 6 whole square. This can be written as 6.67 into 6 into 10 to the power minus 11, and 10 to the power 24 would give you 10 to the power 13 divided by 6.4 into 6.4 into 10 to the power 12. The whole thing is multiplied by 65. If you do calculations for this particular thing, you would get it approximately equal to 9.8, and you have to multiply it with the mass, and this comes out to be equal to 637 Newton. So what did you find it out? What did you find out? What is this value? This value is essentially gm by r square. And what is gm by r square? It is the acceleration due to gravity. Acceleration due to gravity on the surface of earth is how much? It is approximately equal to 9.8 meter per second square. So this is how you get it. You substitute the values of g, m and r square, and you would be getting 9.8. You multiply it with the mass, you get the force, the gravitational force, also called the weight of the body, and here it comes out to be 637 Newton. So my mass is 65 kgs and my weight, or the force with which the earth attracts me towards its center, is 637 Newton. And how much is the force that I exert on the earth? It will be 637 Newton. How much is the acceleration that the earth is going to experience as a result of that? It's going to be very negligible, because force 637 Newton will be equal to mass of the earth into the acceleration. Now the mass is so huge that in comparison to that, this force is so small. Hence the earth doesn't get affected by me, but I do get affected by earth. I have to stay up on the surface of the earth. If I fall, I'll always fall on the surface of the earth. The earth is not going to go down. Okay, so now let's take the next question. Now the next question says that if the separation of between two objects is increased 5 times, how much should the mass of one of the bodies change so that the gravitational force remains the same? So when you make the separation, increase the separation of two bodies, their gravitational force is going to change. So to make sure that the gravitational force remains the same, you'll have to alter their masses. You can either alter the mass of both the objects, or you can also alter the mass of one of the objects to make sure that the gravitational force remains the same. Now this question is about that. It says that if the separation is increased 5 times, how much will be the mass of one of the bodies that needs to be changed? So let us take 2 cases here. Case 1, the body's masses are m1, m2 initially. Let their separation be capital R. What is the force acting on them? Force in case of 1 is what? G m1 m2 by r square, right? What is the case 2? Case 2 is the mass 1 remains the same, mass m2 becomes capital M. We don't know what that would be, we have to calculate it, and the R, the separation becomes 5 times. So the separation in this case is 5R. So what will be F2? It will be G m1 m by 5R square, that is G m1 m by 25 R square. Now as per the question, F1 is equal to F2. The gravitational force doesn't change. So as per question, F1 is equal to F2. What is F1? F1 was G m1 m2 by r square, and this is equal to G m1 m by 25 r square cancels out, G cancels out, m1 cancels out. What do you get? Ms. M becomes 25 m2. So to make sure that the gravitational force remains same when the separation is increased 5 times and one of the masses is kept constant, the second mass has to be increased 25 times. So the body of the second body has to be replaced with a body that's 25 times as big as the mass m2, and then only will you be getting a case where the gravitational force becomes equal despite the separation increasing to 5 times its original value. The next question is about geostationary satellite. What is a geostationary satellite? A geostationary satellite, as the name suggests, is a satellite that is stationary geographically. That means when you send a satellite over the surface of the earth, a satellite that remains stationary with respect to a particular place above which it is stationed, then it is called a geostationary satellite. So you have the earth, you have a satellite that's launched from here, and if this satellite has to always stay right above this place, then it will be called geostationary with respect to this place. It will always stay here. How will a satellite be geostationary? The earth spins on its axis, right? It spins on its axis. When it spins on its axis, and if this satellite also spins together with it at the same speed, then this satellite will remain stationary with respect to this place. So if the whole revolution that the satellite will make, to ensure that it stays at the same place, relatively at the same place with respect to this place, when the revolution of this satellite coincides with the rotation of the earth around its axis, then only will the satellite be called geostationary. So for a geostationary satellite, the period of revolution is same as the period of rotation of earth, which is once in 24 hours. So the geostationary satellite is going to make a revolution around this whole earth in 24 hours, and then in that case it's going to appear stationary for a place on the surface of the earth. So given the options, the third option that says that the geostationary satellite follows the direction of Earth's rotation is correct. If it follows the direction of the Earth's rotation, only then will it appear stationary over a certain place. Now for this question, you have been given that the mass of Jupiter is 1.9 into 10 to the power 27 kg and the mass of Sun is 1.99 into 10 to the power 38 kg. The distance between the centers is given, and you have to find out the speed with which Jupiter moves around the Sun. And we have to assume that the orbit is circular. So now if you recall from what we had studied in the theory, when you whirl a stone around in a circle right above your head, the acceleration that it experiences is v square by r, and the centripetal force is mv square by r. And what is that centripetal force equal to in case of planetary objects? It's going to be equal to the force of gravitation, the gravitational force that's acting, gravitational force. So you have mv square by r, which is the centripetal force, and this is equal to what? This is equal to the gravitational force acting between the Jupiter and Sun. The speed is assumed to be constant. So you have Vj square as the speed of Jupiter moving around the Sun. Here it will be mj. So mj gets cancelled, so you don't need mj at all. R gets cancelled, and you have Vj square equal to Gms by R. And what will Vj be? It will be equal to square root of Gms by R. What is the value of G? It's 6.67 into 10 to the power minus 11. What is the value of M sun? It's 1.99 into 10 to the power 38. You divide it with the radius, the distance that's given, 7.8 into 10 to the power 11 meter per second will be the unit, and if you simplify it, you will get 1.304 into 10 to the power 8 meter per second, which as per the options given is option C. So this is how you do it. So this is the centripetal force. The gravitational force is equal to the centripetal force. We assume that the speed of Jupiter moving around the completely circular orbit of the sun, around the sun, is constant.